chapter 17, we're going to looking at the ester, epoxide, and the sulfide. We actually already have seen esters many times, mainly as the solvent for organometallic compound, green yarn, organolithium. And the reason why we're using ester as a solvent because of the, it's most important thing, it doesn't react with organometallic compound. Second is ethers still have that oxygen atom. Ethers still have that oxygen atom. And this oxygen atom, okay, has two lone pairs. So ethers still can serve as a Lewis base. So it can help, especially in case of Grignard region, help dissolve Grignard region. Lithium also important because both lithium cation and magnesium cation, they are, they have appreciable Lewis acidity. So if you use a solvent, the solvent can help stabilize those metal cation. So that's the major use of ethers we have so far. And anyway, if we talk about ether, what are ethers? Ethers are a class of organic compound with sp2 hybridized oxygen as a key functional group, and that oxygen will be bound to hydrocarbon groups. And both sides will be bound to hydrocarbon groups. So this R1, R2, both of them must be hydrocarbon group. They could be LQ group. They could be, the one LQ group, one vinyl group. The one from alkene or alkyl group, or one alkyl group, one aromatic group, or both aromatic group, or both alkyl group. So basically, must be carbon-based group, and not carbonyl, just hydrocarbon-based group. This is called ester. Okay? And the esters, they are pretty difficult to make them react. And the only exception is epoxide. Okay? Epoxide is actually quite reactive, and we already looked at one type of reaction in chapter 15. That reaction will be tested. So, in a synthesis problem, okay, just give you a hint. Okay? So the why epoxide is so reactive? Can anyone tell me why epoxide is so reactive, but regular ether not reactive? Both have lone pairs, right? So this is epoxide. That is regular ether. What's biggest difference? So the epoxide is very reactive, but this one is not. Okay, this one is not reactive at all. Okay, this one is not reactive at all. Both are cyclic ethers. Okay. So why epoxide is so reactive? Angle strength. Okay. So this, anyway, we're going to talk about the reaction. Mostly we're going to look at a lot of reaction for epoxide, but I hope you know that angle strength. Okay. Sulfide is a sulfur analog of ethers. They have different physical reactions. So nomenclature first. So we're going to basically look at the naming of regular ethers, cycloethers. Forget about it. I'm not asking you to memorize. Yeah?
What did you say the reaction? What word did you use?
Angle strength.
Angle strength?
Yes, basically in this ring, okay, the angle is around a 60 degree. Those angles around a 60 degree, but the angle they wanted is about 110 degree. This 60 degree, but the angle they preferred is 110 degrees. So the large destabilization because of having unfavorable angle. Just like, okay, your arm here is uncomfortable, but if you push your arm in like in this way for extended period of time, you will feel very uncomfortable. Like this, it's just an uncomfortable angle. This way is natural, comfortable. But let's say it's like this, for 2 hours. That's just like what happens in the, the oxide. Okay. Nomenclature of ethers. Cyclic one, forget about it. I'm not gonna ask you. It's just pure memorization. But I do ask you to know how to name regular ethers by substitutive nomenclature or functional class nomenclature. Substitutive nomenclature, if you have, let's say, 2 LQ groups in an ether, we using the LQ group with the longest continuous carbon chain as the parent. And like in this particular case, this example, one side we have the 2 carbon chain, the other side we have 3 carbon chain. So the longest connected carbon chain is from here to here, 3 carbon one. Okay, so the base name is propane. Then the rest of them is a substituent. So this is the base name, okay, propane. Okay, so then these are the 2 substituents. We treat the rest of the substituents. Okay. So those 2 substituents are chloro and this one we call if this one with oxygen we call ester, okay, but with oxygen bound to the ester we call it ethoxy. It's just the name, okay. Those are 2 substituents, ethoxy. It's difficult for you to see. Let's see. I'm gonna write it here. So so first we find the longest continuous carbon chain here, okay? So the base name is propane. Then we identify the 2 substituents. One is called chloro, one is called ethoxy, okay? Means the ETH, okay? If it's just LQ, we call ETHYL, right? Now to connect to oxygen, we drop YL, put the ETH, OXY, ethoxy, okay? So then now we need to create a locus, okay? So for the longest continuous carbon chain, doesn't matter from which end. We always one is the one is 1, the other 3. But in this particular case, if doesn't matter from which end, we always create one locus, while the other is 3. We need to give the lowest locus to the substituent with better alphabetic order. So chloro started with C, okay? It should come before the ethoxy started with E. Okay? So that's why chloro gets 1, the ethoxy gets 3. Okay? This is the one we start with from right side instead of the left side. Okay? So this is called 1 chloro, 3 ethoxy, propane. Okay? Now just give you a very similar name, but it's a bit different. Okay, so if we have a very similar molecule, so again, this one is parent chain, propane. Okay, and they have the 2 substituents, okay, ethoxy and fluoro and ethoxy. Now, because the doesn't matter we start from which end, you always get one locant as 1, the other one 3. But now the SOC group start with E to be given higher preference to receive locant 1 because the other one start with F. Okay, so this one name, so this one is they start from here. Okay, 1, 2, 3. So this one called 1-ethoxy 3-fluoropropane. 1-ethoxy 3-fluoropropane. Now the rest two names, they are pretty straightforward. If you know how to name this one, those two should be very easy. And besides of this substitutive nomenclature, you also can name them by functional class nomenclature. That's even easier. So basically you name the group, okay, individually, okay, then arrange the names of the two groups in the two separate words. They are separated by space, and then arranging alphabetical order, then followed another white space, give a name called ether. Okay, like this one. Okay, suppose we should call ether. Okay, ether and ether, supposedly. Okay, but because those two alkyl groups, they are the same alkyl group, so you can call it diether. Then white space ether. Okay, and in this one, the two groups are different. So one is methyl, one is ether. So we list those names in alphabetic order. So ethyl space methyl ether. Okay. And this guy, the two alkyl groups, one is called ethyl, left side. The other right side, if you forgot it, this is called 3-chloro, the propyl group. Propyl. You can do it here. So if using functional class nomenclature, so basically in functional class I will just rewrite it probably easier. Okay, in functional class nomenclature, basically you get one part alkyl group. Oxygen is a functional class, then another alkyl group. So this one we call the ether. This one we call the 3-chloro propyl group. Okay, because of this one has to be carbon 1 because that's the point of attachment. Okay, for the alkyl group, this is point of attachment. This is called 3-chloropropyl. So the name of this is the alphabetic order. List those groups. 3-chloropropyl, one white space, ether, ether. These are this alphabetic order C, E, okay, and ether. And the sulfide, they can be named by functional class nomenclature, alkyl sulfide. Instead of ether, they call sulfide, or substitutive nomenclature. Instead of the alkoxy, we call alkyl thiol. Okay. So like this one, we can, treat, because the two LQ groups of same length, we can randomly choose one as a parent. So this is ether, the parent name. Then this part, okay, is named as ethyl thiol, okay, ethyl thiol. That's just something to memorize. And for this one, obviously this part has a longer carbon chain, so that's the parent. We call cyclopentane. And then for this part is a functional group. We call, the methyl thiol, okay. And that's, that's the substitute nomenclature. If the functional class nomenclature just list the, the LQ group's names. Like in this case, ether sulfide, because both of them are ether, we just call diether sulfide. And here you have one side is cyclopentyl group, the other part is methyl group, and these two groups named by in alphabetical order and separated by a white space, and then write the word sulfide, and there should be a white space separating the second group name under the sulfide name, just like the ether name. Okay, the bonding in ether is nothing, the strange, because oxygen is single bonded for both groups around it. So the oxygen is sp3 hybridized. Okay, so there's two lone pairs of oxygen and the two, the bonding pairs of oxygen. So the bond angle should be close to 110 degree. But if the both LQ groups are really big, the angle can be a little bigger to release steric hindrance. And the ether oxygen also behave largely like a CH2 unit from the conformation perspective. So basically, we just like, the two lone pairs will behave like a class has another entity. You shouldn't not come in.
What happened?
The class has not ended yet. 9:55 we finish.
Oh, okay. I
So-
can stay here for 3 minutes?
You're at the storming class.
Okay.
Yeah, let's come here to the coming.
No worries.
Okay, so just like this oxygen, you can consider, it's a CH2, but the two CH bonds replaced by two lone pairs. So other than that, it's pretty much, so like this diether ether, its conformation is almost the same as the cyclopentane. Okay, so the most stable conformation is all anti-conformation, but only with one CH2 replaced by oxygen. Similar thing is if you have tetrahydropyrene, don't need to know the name. Myself also don't remember that well. So it's basically this is a molecule, okay? And its conformation is very much like a cyclohexane, like this one. Cyclohexane is basically O replaced by CH2, you get a cyclohexane. And I hope you recall from organic 1, cyclohexane, they almost always exist in the chair conformation. Okay? So the O just replace for one CH2. And the physical properties, the of ethers, can be understood based on its mostly hydrocarbon, but has an actual oxygen atom. And because there are two lone pairs on the oxygen, so this oxygen makes the ether capable of serving as a lowest base, and can form hydrogen bond with a water molecule, basically acting as a hydrogen bond acceptor. So ether has a bit, okay, water solubility, but the ether itself, it cannot form hydrogen bonds because of It only can provide hydrogen bond acceptor, but no hydrogen bond donor. So ethers, the boiling point is just like hydrocarbon. So actually, the diether ether boiling point almost same as pentane. It just O is replaced by CH2. But obviously, ether, diether ether has much higher water solubility than pentane because of this O can accept, hydrogen bond from water. So that's just something about physical property.